We've talked about the elements, the solvents, and everything that we need for the substitution reactions, the nucleophilic substitution reactions. So now let's talk about what they are and how they actually happen. So in a nucleophilic substitution reaction, what's going to formally happen is that we have an RX bond. Remember, this is an alkyl halide. I was going to say alkyl bromide, but they can be any other of the halogens actually. So it's alkyl halide. Then we have a nucleophile, and then after the reaction, that nucleophile is going to substitute the leaving group, that is that X. During that reaction, this Rx bond is going to break and then a new bond is going to form. And both of those bonds are sigma bonds. What happens is that the nucleophile will attack here the R, and then the leaving group will actually leave. But this, in theory, can happen at three different timings. The first one is that the bond forming and the bond breaking happens at the same time. The second one is that you break this bond first and then the nucleophile can attack. And then the last one is that the nucleophile attacks and the leaving group leaves after that. So let's explore these three possibilities. The first one is that all happens at once. And so this is what we call a concerted mechanism right here. And what happens is that the nucleophile will attack right there to the electrophile, because remember that carbon right there is electron deficient, and that will kick literally the leaving group out, which is my X minus. So that will happen in one step. And so because it happens in one step and it happens just at once, we will say that this is a bimolecular reaction. If you recall from last week's class, we said that when a reaction happens in such a way that both my reagents are involved in the reaction, then we're going to define the rate as a K multiplied by the concentrations of the reagents of both of them, right? So this will be, and here I would have the alkyl halide. So because the rate will be determined by the two of them and they will be elevated to 1, that will be 1 plus 1 equals 2. That's why we would call a bimolecular reaction, because both of the reagents are involved and the order of the reaction is 2. And so the rate of the reaction is second order. This is one option. And this is what we actually called an SN2 type of reaction. Because the reaction happens in one step and both of the nucleophile and the alkyl halide are involved, these two is the same two that we're going to keep talking about in the SN2 type of reactions. The other possibility is that the leaving group leaves first, giving us an intermediate such as this one, the carbocation, and then the nucleophile can simply come and attack and give us the final product. This mechanism goes through step 1, the leaving group leaving, and step 2, the nucleophile attacking. Now, the rate determining step is going to be this step right here. And why is that? Well, because for this sigma bond to break, it's going to take a lot of energy, and so that is the one that is going to take it's going to have a really high activation energy. Remember in those energy diagrams we were talking about, that is it's going to need a lot of energy for this to happen. However, this second step is going to be really quick because we have a plus in the carbocation and a minus in the nucleophile. We usually have a minus, but we can also have like electrons, and that reaction is going to happen really, really quick because they're just going to snap together. So the first step is going to be my rate determining step because it's low. And because of that, my rate, as we were talking about rates the other day, so my rate is K times only the Rx, which the Rx is the alkyl halide right here. The rate only determines on this first reagent because this is going to be so slow that this second part is going to be negligible. So as soon as this reaction is ready, this reacts right away. But this takes time to happen. So this will be my rate determining step. And because my rate only depends on the alkyl halide, we say that this is a first order reaction because there is only a 1 right here. And as you may guess, this is now going to be called an SN1 reaction. It's very counterintuitive because the reaction happens in 2 steps, but we call it an SN1. And the reason for that is because this 1 doesn't come from the fact that it goes through 2 steps. It comes from the fact that there is only one of the reagents involved into the rate. And finally, the last option is that the nucleophile attacks, gets together, and then the leaving group leaves. But that is not possible. The reason why that is not possible is because this carbon is already connected to 4 things. Now, if the nucleophile were to come and attack and form a bond, then that carbon right there will be exceeding the octet. And you know that it's not possible in organic chemistry. That's one of our biggest rules. The second row elements cannot exceed the octet. So then this reaction is never going to happen through this mechanism. So here, let's look at 2 examples. What they are saying here is kinetic data shows that the rate of the reaction 1, this reaction right here, depends on the concentration of both my reactants, which suggests that it's a bimolecular reaction with a one-step mechanism, right? So what type of reaction is this going to be? If it's bimolecular, it's going to be SN2, and it's going to happen all in one step. What that means is that my nucleophile here, the acetate, the lone pair in the acetate, is going to come and attack that carbon, and the carbon Br group, the carbon Br bond is just going to leave right away. And so as one comes, the other one is going to go. And we're often gonna be talking about transition states, right? So if you want, I can draw you here. So imagine we have carbon, carbon, carbon. So my transition state is going to look, so as the Br leaves, my nucleophile, that it's this thing right there. As the nucleophile is approaching, the Br is leaving at the same time. So this will be my transition state for you to picture it. And all of this is going to happen in one step. We're going to talk about this later on, but this nucleophile has to attack from the back of the reaction to be able to kick the Br as hard as possible. So think about it as if you're playing pool. You want to hit the white ball as straight as you can, as straight from the back, to kick the next ball as hard as you can, right? So think about it in terms of playing pool. This will come from the back, and then this will kick the Br as quickly, as hard as possible. We'll talk about it in an upcoming video. And the other option is that kinetic data shows that the rate of the reaction 2, this one, depends on the concentration of only the alkyl halide. If it only depends on the concentration of one of the reagents, then this reaction is going to be unimolecular, right? So if it only depends on one, it's going to be an SN1 type of reaction. And if it's an SN1 type of reaction, it's going to happen through an intermediate. Okay, so I'm going to show you here that intermediate. So this is the reaction as we have it. Here we have the acetate. That's a minus. Okay. And then that will give us the exact same product that we got for the previous reaction. That and that, right? Let's just make sure. Yes. Plus the Br. And this is a double bond, okay? So if this happens through a mechanism that needs two steps, the first step okay, here we go. The first step is going to be the leaving group leaving, right? So this is the first step where the Br leaves. And now the second step is going to involve the nucleophile attacking. And so now my nucleophile can attack negative charge, positive charge. This is going to happen very quickly, and that will give us our products. So first step, leaving group leaving. Second step, the actual nucleophilic attack.